0.2 divided by 2. Okay, so this is your width, this is your depth, this is your y bar. Okay, so y3 divided by 2, the whole thing is 3 inches divided by 2. This is 0.2 divided by 2. So this will be equal to 2 minus 0.3 minus 0.3 minus 0.3 times by 0.2 times by 3 over 2 minus by 0.1. So it's equal to 0.392 inches cubed. Okay, so you have the shear at point B is equal to V over I multiplied by Q 0.392 divided by the thickness, which is equal to 0.2. And then you have to do a 2 down here. Why 2? Because one arrow go towards the left, the other one arrow go towards the what? The right. Okay, so you have to do the 2 over there, right? So this will be equal to 0.392 divided by 0.2 divided by 2 is equal to 0.98 V over I. Okay, so this is the shear stress at point B. Now, given, okay, we are given that tau max is equal to 0.3, right? We are given that tau max is good. So the next one we want to find is, so I'm going to copy the whole thing again. So either thin wall or thick wall, right? Tau max, right? Tau max is going to be at point C. The tau max is going to be at point C. It's going to be at a centroid, point C. Okay. So we're going to find tau max. We know that tau max is equal to the shear at point C. Yes or no? And we know that this is equal to 10 times 10 to the power 3 psi. Okay, we know that this is 10. Is it 10? Let me see here. Yep, 10 times 10 to the power 3 psi. Now, what I want to show you is, hey, why don't we do this? Okay, we try to analyze from the top and we try to analyze from the bottom. Okay, so we're going to analyze from the top. Means analyze from the top. I'm going to use this view down here. So we're going to analyze from the top. Okay, we're going to analyze from the top. So I'm going to copy this view. And we're going to paste here. Right? So this is from the top. And we know that we're going to analyze from the top. Right? And the box beam thin wall analysis. So we're going to apply box beam wall analysis. Okay, thin wall analysis. And because it's box beam, which I did not emphasize earlier, because it's box beam, right? The Q, once moved towards the left-hand side, one moved towards the right-hand side. That's why when it's box beam, you will write down, to reduce your confusion, you have to write down it's going to be what? 2Q. Why 2Q? One goes towards the left, and the other one goes towards the what? The right. Okay, so this is box beam analysis. Okay, so we are going to look at our Q first, right? So the Q now. So again, the formula is equal to shear is equal to VQ over IT. And we know, regardless of whatever position we look at, VI is going to be constant. So the thing to do now is we're going to look at Q. So it's going to be Q of the flange which we found already, plus by Q of the web. Okay, Q for the flange we found is equal to 0.392 plus by Q of the web. So we have two web down here. So this is for the left and right. All right. So the width will be equal to 0.3. The depth is equal to 1.5. The Y bar is 1.5 divided by what? 2. Okay, so this is equal to 1.5 divided by 2. So this turned out to be equal to, so it's equal to 0.392 plus by 2 times by 0.3 times by 1.5 times by 1.5 divided by 2 is equal to 0.675. So this will be equal to 0.392 plus by 0.75. So it is 1.067. Okay, inches cubed. So from here, the shear stress at point C is equal to V over I are constant. All right, V over I are constant. The Q is 1.067 and the thickness is 0.3. And you multiply by 2 because you have what? Left and right Q, right? One Q goes towards the left, the other Q goes to the right. Okay, so this will be equal to 1.0 divided by 3 divided by 2. So it's equal to 1067 divided by 600 V over I. And then we know that this will be equal to what? This will be equal to 10 times 10 to the power 3. So the V over I is equal to 10 power 3 times by 600 divided by 1067 is equal to 5.623 times 10 to the power 3. Okay, and the units is pounds per inch to the power of 4. Okay, why I calculate V over I over here? Because this is only the shear stress that I know. And remember what I told you, V over I is constant regardless of the position, right? Rule number 1. Okay, now the next thing I'm going to do now, right? I'm going to now try, we're going to try to do the analysis. Okay, we're going to do the analysis. I'm going to draw a vertical line. Okay, we're going to do our analysis from the bottom now. Okay, so we're going to do our analysis from the bottom. Right, so I'm going to cover the top. All right, so we're going to do our analysis from the bottom. And we know when we do our analysis from the bottom, it's no more a what? It's no more a white flange. So, sorry, it's no more a box beam. Okay, so what we have now is a white flange. So we carry out with a white flange. Okay. Okay, this is a white flange beam section now. And then because the shear flow, right, the Q on the left did not originate from the right, they're not shared. Okay, so that's where now it's only Q. And the T is equal to what? 0.3. Okay, then the shear force, hey, what did I do now? I do apologize. So now we want to find the Q, right? So the Q will be the Q of the flange plus by Q of the web, right? So again, the centroid is at the datum's at the centroid. We're going to start from y max. So I'm going to divide this into 2. Okay, so that's the way I'm going to divide it. So this is section number 1. This is section number 2. So this section number 1 is my flange. Right? And there is my web. Okay. So Q flange. So the flange, the thickness will be, the width will be 1 minus by 0.3. The depth is 0.2. Right. So this will be equal to 1.5 or 3 divided by 2 minus by 0.2 divided by 2. Now, what is critical now is I don't need to multiply by what? I don't need to multiply by 2. Because the Q starting from here is independent from the Q on the what? On the left-hand side. The Q on the right-hand side is independent from the right-hand. They don't have the same point of origin. When it's a box beam, there is a common point of origin. When it's on a white flange, there's no common point of origin. One is on the left, one is from the right. That's why you don't need to multiply by what? 2. Okay, that's where you have to be very clear down here. So the next one is the web. The width is 0.3. The depth is 1.5. Then multiply by 1.5 divided by 2. So this will be equal to 1 minus 0.3 times 0.2 times by 1.5 minus 0.1. So this is 0.196 plus by 0.3 times 1.5 times 1.5 divided by 2, 0.3375. So this will be equal to 0.196 plus by 0. Yes.
Isn't the width of the web 0.2, or is that covered? Like the
web.
The width of the web 0.3.
Yeah, it's 0.3 because it's 1 inch minus by 0.7.
Oh, okay. Yeah.
Okay. So this is 0.55 5335 inch to power Q. Right. So your shear stress at point C is equal to V over I common. The Q is what? The Q is equal to 0.5335, and then the thickness is equal to 0.3, right? So this will be equal to 0.5335 divided by 3. So this will be equal to 1067 divided by 600 V over I. So this will be equal to 100 times 10 to the power, 10 times 10 to the power 3. So therefore, V over I is also equal to 5.623 times 10 to the power 3 inch pound per inch power 4. So what you see over here, either to find your tau max, you start from the top, on the bottom is the same. The most distinct thing is this. For a box beam, it's equal to 2Q. Okay. For analysis for white flange is only equal to what? To Q. Okay. I'm going to stop here now, and I hope you all will start with your quiz. Okay. Anyone, any questions so far? Anyone? No question? I can see some of you left already starting your quiz. Okay. So your quiz is due at 3 p.m. Okay. So I'll see you guys next week. Thank you.